Episode 9, Life Conquers the Land, Plants, Insects, Amphibians Spread. Part 1, The Ordovician Seas and the Green Revolution. Introduction, the Second Surge.
After the turbulence of the Cambrian, Earth did not fall silent. Around 485 million years ago, the Ordovician period began, bringing the second great expansion of biodiversity. The seas, already busy with trilobites, brachiopods, and mollusks, became richer and more structured. New reefs rose from the seafloor, plankton filled the sunlit waters, and the chemistry of the oceans and atmosphere shifted yet again. Out of this marine abundance came a quieter but world-shaping development, the first true greening of the continents. The Great Ordovician Biodiversification Event, GOBE, between about 470 and 445 million years ago, multiplied known marine genera several-fold. Ordovician rocks record the rise of articulate brachiopods, bryozoans, corals, nautilurid cephalopods, and planktonic graptolites. Geochemical data suggest that global oxygen levels stabilized at roughly half to two-thirds of modern values, enough to sustain large, active animals and intricate ecosystems.
The Ordovician Oceans.
The early Ordovician world was warmer and wetter than before. Gondwana sprawled across the southern hemisphere, while Laurentia and Baltica lay near the equator. High sea levels flooded the edges of continents, creating broad, shallow seas that acted as vast nurseries of life. Sunlight, warmth, and nutrient-rich runoff turned these epicontinental seas into fertile incubators. In these waters, plankton flourished. Radiolarians, silicious plankton with delicate skeletons, appeared and began to draw silica from seawater. Green algae and early dinoflagellate relatives crowded the upper layers of the ocean, forming the first truly complex planktonic food webs. Below them, oxygenated waters allowed animals to spread into habitats that had been chemically hostile in the Cambrian. Ordovician black shales contain elevated concentrations of redox-sensitive metals such as molybdenum and uranium, while carbon isotope values indicate vigorous burial of organic matter. Together, these signals point to a stable, oxygen-rich, high-productivity oceanic system, the energetic foundation for life's next steps.
The Reef Builders.
Among the most dramatic Ordovician innovations were the first long-lived coral stromatoporoid reefs. Where Cambrian reef builders had flickered and failed, new organisms succeeded. Tabulate and rugose corals, working alongside calcareous sponges and microbial communities, constructed immense reef complexes that stretched for kilometers along tropical shelves. These reefs stabilized sediments, broke waves, and created a labyrinth of caves, ledges, and channels. Reefs transformed marine ecology. They offered shelter from predators, nursery grounds for juvenile animals, and hard surfaces for filter feeders and grazers. Life no longer merely carpeted the seafloor, it now built three-dimensional cities in stone. Within these crowded structures, competition and cooperation drove further diversification. The spread of reef systems intensified the global carbon cycle. Photosynthesis in shallow waters, combined with rapid carbonate deposition, drew atmospheric carbon dioxide down from extreme greenhouse levels. By roughly 460 million years ago, concentrations had fallen enough to begin a long cooling trend that would eventually contribute to Ordovician glaciation.
The Green Edge. Life creeps onto land.
While the seas flourished, subtle changes along the coasts hinted at a new frontier. On damp tidal flats and river margins, thin films of green began to spread. Microscopic algae, already comfortable in intertidal pools, clung to wet rock and mud. In partnership with fungi, they formed sheet-like mats capable of trapping dust and moisture. These were the humble ancestors of all later forests. Spores preserved in mid-Ordovician sandstones show durable walls and characteristic trilete marks, signatures of embryophytes, true land plants. Chemical biomarkers from the same rocks confirm photosynthetic activity on land, pushing the origin of terrestrial flora tens of millions of years earlier than once thought. Associated fungal remains suggest that lichens and early mycorrhizal partnerships helped these pioneer plants endure desiccation and nutrient-poor substrates.
The atmosphere begins to change.
Though barely visible from afar, these coastal green films began to alter the air itself. Each photosynthetic cell captured carbon dioxide and released oxygen. When storms washed fragments of this biomass into rivers and ultimately the sea, some of that carbon became buried in sediments rather than recycled. Over millions of years, the effect accumulated. Oxygen levels crept upward. Carbon dioxide declined a little more. Enhanced weathering from plant fungus mats also leached phosphorus and other nutrients from bare rock. Washed into the oceans, these nutrients fertilized marine phytoplankton, which in turn drove further organic burial and oxygen release. A feedback loop was underway, land plants and marine microbes working together to reshape the planet's chemistry.
Prelude to a crisis.
The Ordovician prosperity did not last. By 445 million years ago, continued carbon dioxide drawdown and continental configurations favored the growth of ice sheets on Gondwana. Global sea level fell, shallow seas retreated, and reef communities collapsed. Roughly 85% of marine species vanished in the first great mass extinction of the Phanerozoic. Yet the biogeochemical systems forged at this time, the links between land plants, weathering, and climate, survived and would underpin future recoveries.
Part 2. The Silurian Transition, from Water to Land. Introduction. After the ice.
When the Ordovician Ice Age ended around 443 million years ago, glacier melted and seas once again flooded continental margins. Warm, shallow waters welcomed the return of reefs and the diversification of marine life. Trilobites, brachiopods, and corals radiated into newly open niches, while jawed fishes and giant sea scorpions prowled the water column. Along the shorelines, however, an even more radical transformation was underway. Plants and animals were beginning to build the first true terrestrial ecosystems. The Silurian period, 443 to 419 million years ago, was a time of post-extinction recovery. Coral, stromatoporoid reefs expanded, and vertebrates with jaws and paired fins appeared in abundance. Climate models indicate warm, humid conditions and high but declining carbon dioxide levels, environments well suited to colonization of coastal lowlands by photosynthetic organisms.
The first terrestrial pioneers.
The early Silurian continents were still harsh landscapes, bare rock surfaces, thin protosoils, and pools that dried with the seasons. Yet in sheltered hollows, the first recognizable land plants took hold. These were tiny, leafless stems branching from creeping mats. Each upright shoot ended in a sporangium that released clouds of spores into the air. Filamentous rhizoids anchored the plants to the substrate and helped wick up water. Genera such as Cooksonia and Baragwanathia reveal the anatomical breakthroughs behind this advance. Simple vascular tissues enabled efficient water transport and mechanical support, allowing plants to grow taller than a few millimeters. Even so, early stands rose only centimeters above the ground. The continents were still mostly brown and grey, with scattered patches of green around streams and deltas, but the principle had been established. Photosynthesis could now proceed on land, drawing energy directly from sunlight without the cushion of standing water.
The partnership with fungi and the birth of soils.
The conquest of land depended on alliances as much as anatomy. Beneath the first plants spread networks of fungal hyphae. These mycorrhizal partners penetrated mineral grains, releasing acids that dissolved rock and liberated phosphorus, iron, and trace metals. In exchange, the fungi received sugars from their plant hosts. Together, they formed a single functional unit, capable of exploiting substrates that neither could use alone. As these plant fungus carpets thickened, they began to create true soils. Rock fragments broke down into clays. Organic matter accumulated as litter and microbial biomass. Pore spaces trapped water and air. Even thin, patchy soils acted as sponges, smoothing out floods and droughts and providing a more stable platform for later vegetation. For the first time, land surfaces hosted self-sustaining ecosystems with internal nutrient cycles.
The invertebrate explorers.
Plants did not remain alone on the Silurian shore. Invertebrates followed, attracted by detritus and algal scum. Millipede-like myriapods, primitive arachnids, and early relatives of springtails crept through the damp litter. Their jointed limbs and wax-coated exoskeletons prevented desiccation and provided support in gravity's full pull. Some grazed on microbial mats, others fed on decaying plant material. Trace fossils, delicate trackways crossing ancient mudflats, show that these animals walked on surfaces exposed to the air rather than submerged in shallow pools. They were the first air-breathing animals, using tracheae to deliver oxygen directly to their tissues. With them, a simple but complete land-based food web emerged: primary producers, decomposers, and small consumers linked by flows of energy and nutrients.
The Silurian air.
With photosynthesis now occurring on land as well as in the sea, the composition of the atmosphere shifted again. Oxygen levels rose to perhaps a fifth of modern concentrations. Carbon dioxide continued its slow slide. Lightning, storms, and even the first wildfires responded to this changing mixture of gases. By the end of the Silurian, Earth's atmosphere had acquired a modern-like oxidative potential. The continents were still only lightly greened, but the stage was set for much larger organisms to thrive in open air.
Part 3: The Devonian World, Forests, Fishes, and Amphibians. Introduction: The Age of Green and Bone.
By the dawn of the Devonian, around 419 Ma, the balance between land and sea had changed once more. The continents, especially in equatorial regions, now carried extensive belts of vegetation. River valleys supported dense mats of plants, early insects scuttled among stems, and freshwater fishes filled the streams. The Devonian is often called the Age of Fishes, but it was just as much the age of the first forests and the first-limbed vertebrates.
The rise of forests.
Earlier plants had hugged the ground, limited by weak tissues and simple plumbing. During the Devonian, they evolved lignin-reinforced cell walls, complex vascular systems, and branching trunks capable of supporting large crowns of foliage. The earliest trees, such as Archaeopteris, reached heights of 10 meters or more. Their woody stems, deep roots, and shedding fronds created the world's first true forests, shaded, humid environments radically different from the open Silurian lowlands. Forest growth transformed Earth's surface. Roots stabilized riverbanks and encouraged rivers to meander rather than braid. Thick leaf litter accumulated on the ground, feeding fungi and invertebrates and building deep, organic-rich soils. Lignin-bearing wood decayed slowly, and much of it ended up buried in sediments, locking carbon away for geological timescales. As a result, atmospheric carbon dioxide fell and the climate cooled.
The Age of Fishes.
While forests conquered the land, the oceans and rivers underwent their own revolution. Fishes diversified into a spectacular array of forms. Heavily armored placoderms dominated many marine ecosystems, including giants such as Dunkleosteus with powerful biting plates. Cartilaginous fishes explored the open seas, while bony ray-finned and lobe-finned fishes experimented with new body plans and modes of life. Among the lobe-fins, evolution was quietly preparing for a move onto land. Their paired fins contained sturdy internal bones, precursors of humerus, radius, and ulna. Some developed lungs and nostrils that allowed them to breathe air in oxygen-poor waters. Fossils such as Eusthenopteran and Tiktaalik capture intermediate stages in this transition. Fish with limb-like fins, mobile necks, and flattened skulls suitable for life in shallow streams and swamps.
The insects take wing.
On land, arthropods diversified alongside the plants. By the mid-Devonian, the first true insects appeared, some already possessing wings. These early flyers exploited the still air above forests, becoming the first animals to claim the aerial realm. Their appearance opened an entirely new dimension of ecological interaction, from spore and pollen transport to aerial predation, and further tied the fate of land plants to that of animals.
The amphibian frontier.
Late in the Devonian, some lobe-finned fishes took the final steps onto land. Seasonal droughts, crowded swamps, and unstable shorelines favored animals that could haul themselves from pool to pool or lie in ambush at the water's edge. From these pressures emerged the first tetrapods, vertebrates with digits instead of fin rays. Acanthostega and Ichthyostega, known from Greenland, carried limbs with multiple digits, robust vertebral columns, and lungs supported by rib cages. They still retained internal gills and fish-like tails, and probably spent much of their time in shallow water, but they could walk or crawl on solid ground. Trackways from Poland suggest that tetrapod-like animals were experimenting with terrestrial locomotion even earlier. For the first time, vertebrates joined plants and invertebrates in the continental realm.
The new web of life.
By the end of the Devonian, terrestrial ecosystems had become richly interconnected. Forest canopies intercepted rainfall and fed complex river systems. Soils regulated water flow and recycled nutrients. Insects and other arthropods fed on plants and each other. Amphibians hunted along swamp margins and forest floors. Fires periodically swept through dry seasons, clearing vegetation and opening space for regrowth. The continents themselves now pulsed with the full rhythm of life: photosynthesis, respiration, decay, and predation. To an observer watching this transformation in fast forward, the Ordovician to Devonian would look like a slow but relentless tide of life moving out of the ocean. First a faint green stain along shorelines, then scattered tufts on riverbanks, then low carpets creeping inland, and finally dark belts of forest following the paths of water across the continents. At every step, animals followed. Tiny arthropods first, then insects and amphibians, each wave of colonists testing the limits of air, gravity, and dryness. Seen from space, the changes would be just as dramatic. The blue-white planet of the early Paleozoic acquired swirls of brown and green along its coasts, then deep interior smudges where forests took root on upland plateaus. Seasonal cycles intensified as vegetation altered how continents absorbed and released heat. Clouds gathered differently over wooded regions, and rainfall patterns shifted in response. In this sense, the Devonian did more than add life to land. It turned the continents into dynamic parts of the climate system rather than passive slabs of rock. For evolution, the opening of the terrestrial realm was like adding extra dimensions to a game board. Animals and plants that had once interacted only in two-dimensional seafloor communities suddenly had access to height, tree trunks, canopies, burrows, and riverbanks. New ecological roles appeared: canopy browsers, forest floor scavengers, ambush predators waiting at the water's edge, aerial hunters pursuing winged prey. The diversification of form and behavior that followed would, over the next 100 million years, give rise to ecosystems recognizably similar in structure to those of today, even if their cast of species was entirely different.
Part 4: Legacy and Climate Crisis. The Late Devonian Extinction. Introduction: The greenhouse unravels.
Yet the Devonian triumph contained the seeds of crisis. As forests spread and soils deepened, weathering rates soared. Rivers carried unprecedented loads of nutrients into coastal seas. There, plankton blooms flourished and then died, their decomposition stripping oxygen from bottom waters. At the same time, the drawdown of atmospheric carbon dioxide cooled the climate, encouraging glaciation on Gondwana. The ocean, once the secure cradle of complex life, began to falter.
The geochemical engine of collapse.
The late Devonian extinction, unfolding between about 375 and 359 million years ago, was not a single blow but a drawn-out sequence of crises. Widespread deposition of organic-rich black shales records repeated intervals when large regions of the ocean became anoxic or even euxinic, devoid of oxygen and loaded with hydrogen sulfide. Reef systems collapsed, many placoderm fishes disappeared, and long-stable trilobite families vanished. Two pulses stand out. The Kellwasser event, around 372 million years ago, devastated reef communities. The later Hangenberg event, near the Devonian Carboniferous boundary, eliminated many remaining fish lineages and reshaped vertebrate evolution. Behind both lay the same engine: nutrient-choked, oxygen-starved seas linked to the success of land plants and the cooling of the climate.
Oxygen, fire, and survival.
Paradoxically, while the ocean suffocated, the air above them may have become highly oxygenated. Extensive forests and the burial of their remains drove atmospheric oxygen to levels comparable to or perhaps exceeding modern values. Charcoal fragments in late Devonian rocks show that wildfires became frequent features of the landscape. These fires reduced forest cover, accelerated soil erosion, and supplied yet more nutrients to the oceans, tightening the feedback loop that underpinned the crisis. Life, however, endured. On land, plant and insect diversity rebounded within a few million years. In the seas, new reef builders and fish groups emerged. The surviving lobe-finned vertebrates would give rise to amphibians, reptiles, and ultimately mammals. The catastrophe acted as an evolutionary filter, pruning some branches while allowing others to flourish.
Conclusion: the living continents.
By the close of the Devonian, Earth's continents had been permanently transformed. What began in the Ordovician as microscopic green films on damp rock had become forests that reshaped rivers, soils that altered climate, and animal communities that filled land, water, and air. Plants, insects, fishes, and early amphibians together created a fully integrated biosphere in which atmosphere, hydrosphere, and lithosphere were tightly bound by life. The price of this progress was instability. The same feedbacks that cooled the planet and enriched the air could, when pushed too far, suffocate the seas and trigger extinction. Yet through these crises, the planet learned to regulate itself more effectively. Weathering climate feedbacks and biologically driven carbon cycles, tested in the Devonian, would keep Earth broadly habitable for the rest of its history. Above all, these Paleozoic innovations established principles that still govern the modern world. Plants linked rock to air through roots and leaves. Fungi and microbes closed the loop by returning nutrients from dead tissue to the soil. Animals stitched habitats together by moving energy and matter across boundaries. Once these feedbacks were in place, later radiations of reptiles, dinosaurs, birds, and mammals could unfold on a planet whose basic operating rules had already been set by mosses, club mosses, and the first forests of the Devonian. In the next episode, the story will continue into the Carboniferous and Permian, ages of coal forests, giant insects, and the first true reptiles, where the greening of the continents reaches its zenith before another reckoning reshapes the world again.